Section 3.6, Fundamental Sets of Solutions. Over the course of previous sections, we've determined how to find the general solution to a second-order LHCC differential equation in every possible case. That is, for every possible type of root or roots the characteristic polynomial could have. There were three types of roots: real and distinct roots, complex conjugate roots, and a real and repeated root, and we addressed all three types. In each case, our general solution was built as a linear combination of two specific solutions. We always found a y1 and a y2, then we combined them to create our general solution. As we did, we often made reference to whether the solutions were, quote, nice enough, as our author said, or if the two solutions were distinct enough, as I said. In this section, we finally formally derive and define the relationship that we've been talking about in quotation marks for a couple of sections. Let me first remind you of two important ideas we've encountered in previous sections. First, once we have a solution or two to our LHCC diff-EQ, we can essentially endlessly construct additional solutions using these two key facts. First, any scalar multiple of a known solution is also a solution. And then the sum of any two known solutions is also a solution. So as indicated here, if I had two solutions, e to the 4t and e to the negative 2t, I don't know what the differential equation is, but I'm just imagining that these functions are solutions. Then using these above two facts, I know that I could just spend the rest of my life building new functions by just either multiplying by a constant. So since e to the 4t is a solution, 7 e to the 4t will be a solution. So negative 3 e to the 4t. I could multiply this second one by a constant. I could multiply them by constants and add them together, etc. As I say here, this list is literally endless. So the idea is that any given differential equation, especially in this particular form, has infinitely many solutions. And we can build them from known building blocks using these two facts. Secondly, the general solution is different from any of these specific solutions we were just discussing. And in fact, it's somehow meant to encapsulate all of the specific solutions into one general form of solution. And in order to construct this general solution, we've repeatedly mentioned the building blocks must be, quote, distinct in some appropriate way. This distinctness is exactly what I mentioned a minute ago. Our author calls two such functions nice enough. Here's the formal name for what's going on here. We call two functions that can be used to build the general solution of our LHCC differential equation a fundamental set of solutions. As I've described here, this is exactly this property of being nice enough or being distinct that has been referenced in previous sections. This raises the question, if I have a pair of solutions that could potentially be a fundamental set of solutions, how do I check? Well, introduce a tool. It's kind of got a weird name. It's called the Wronskian, and this tool serves exactly this role. In this final paragraph on the first page, I briefly mentioned the idea of a basis from linear algebra. I believe some students have already completed a linear algebra course, so you should have encountered this idea before. If you haven't, that's fine. I just quickly mentioned it here in order to try to relate this to what some students may have seen in another class. This idea won't be an essential part of how we approach these problems, but I do think it's an interesting connection, so that's why I wanted to spend a paragraph talking about it. All right, on a recent homework problem, I had you imagine an LHCC ODE that had this as the general solution. Then using totally general initial conditions, I asked you to solve for the coefficients C1 and C2. Hopefully you made the appropriate substitutions into y and y prime. You did some sort of algebra, maybe substitution or elimination, to solve the resulting system of equations. What I want to do is make things even more abstract. I want to just call my two solutions y1 and y2. I'm not going to speculate a specific form of function for those solutions. And then I'm just going to state that my general solution would be C1 times Y1 plus C2 times Y2. I'll once again use generic initial conditions. I'll just plug an arbitrary initial t value into y, say t sub 0, and I'll call the corresponding output y sub 0. and then plugging that same arbitrary initial t value into y prime, I'll call the output y prime sub 0. Once again, I get a system of equations, and I could use substitution, elimination, maybe matrix methods to solve this system. But there's a specific point that I want to prove. So instead, I want to use a technique called Cramer's rule. As I've mentioned in this paragraph here, I'm essentially asking what has to be true about these numbers, y sub 1 of t sub 0, y sub 0, all the rest, in order to actually be able to solve for C1 and C2. That's ultimately my goal. And as I said, I want to apply this theorem, this is called Cramer's rule, in order to be able to think about the structure of the process that I would use to find these solutions. You may or may not have seen this theorem before, but if I have a generic 2x2 system, Cramer's rule states the solutions of the system directly in terms of the original coefficients. It's kind of like the quadratic formula in a way. It just tells you straight away what the solutions are. These tall vertical lines indicate the determinant of the little 2x2 matrix. You remember a 2x2 determinant? I multiply across one diagonal, and then I subtract the product along the other diagonal. So there's kind of a lot to do here in terms of the actual calculations. And in truth, I don't want to use Cramer's rule to actually solve the system. I just want to observe something about the structure of Cramer's rule. Notice that both of the denominators in Cramer's rule are the same, and we will clearly not have solutions to the system if these denominators equal 0. If this denominator, though, is any number except 0, the system, the corresponding system of equations, will have solutions. So on the top of the next page of the notes, I state the general idea. So that denominator expression that shows up in Cramer's rule can be used as a tool to determine if any 2x2 system has solutions. This is true for any 2x2 system, but we have a specific system in mind. Let's go ahead and find that Cramer's rule denominator for our system. Here it is. You have to back up and look at the components of our system to verify that this is the determinant prescribed by Cramer's rule. This is the determinant that we would get in the denominator if we were going to use Cramer's rule to solve our system. So, given two solutions of a second order LHCC differential equation, if this expression is not 0 for some t sub 0 value, then the system will have solutions, the system of linear equations. We will be able to solve for C1 and C2. We don't actually just want solutions for like some isolated t sub 0 values. So we want this expression to be non-zero on an interval of t values. So this little 2x2 determinant built from the components of our system of equations is exactly the tool that we can use to check if two solutions are nice enough or distinct. Basically, if two solutions form a fundamental set of solutions for our differential equation. Here's the name we give this tool. It's called the Wronskian. Notice the Wronskian is an operation performed on two functions, and it's evaluated at the input t sub 0. And it's exactly what we just saw we would get from Cramer's rule in the denominator. As I've noted here, while it technically should be evaluated at a specific t sub 0 value, we typically just write it more generally like this, then look at the quantity or expression that results and consider it for a range of potential t values. Theorem 2 here summarizes what I've been saying. If y1 and y2 are two solutions of the LHCC ODE A y double prime plus b y prime plus cy equals 0, then those two functions, y1 and y2, form a fundamental set of solutions for this differential equation on any interval on which their Wronskian is non-zero. So just to reiterate, our goal is to have a non-zero value for the Wronskian, and if we can identify an interval of t values on which that's true, then those two functions, the two solutions that we had identified previously, form a fundamental set of solutions. Let's jump into an example. Example 1, we've got pretty familiar looking ODE, y double prime plus y prime minus 6y equals 0. Pretty friendly second order LHCC ODE. So I'm not worried about how to find the solutions. My focus on this problem is instead to use the Wronskian and look at the value of the Wronskian expression and use that to determine whether or not the two given functions could serve as a fundamental set of solutions. So from above, we have this definition of the Wronskian in general, and we can plug in the ingredients that we've been provided in this specific example. Here I've just plugged in the y1 and the y2 and then their appropriate derivatives. And then recall that these tall vertical lines indicate the determinant of this 2 by 2 matrix. And a 2 by 2 determinant is given by this simple little pattern. I multiply down across this diagonal, and then I multiply this diagonal, and I change the sign on this product. Let me perform that operation. So multiplying across this way, I'll get negative 21 e to the negative 3t times e to the negative 3t. Those two exponentials, I can combine the exponent by adding them. So I have negative 21 e to the negative 6t. Something similar across this one. Notice here that I've got negative 3 times 7. So that's where I got this negative 21. But then by the definition of a 2 by 2 determinant, I change the sign on that term, or you can think of subtracting that term. And simplifying, I see that the Wronskian in this case equals 0, and it's identically 0, which means it's 0 for all t values. Now remember where the Wronskian comes from. It is the denominator in Cramer's rule, in the two fractions determined by Cramer's rule. So what that's telling us in this case is if I was to try to use these two solutions to solve for C1 and C2 in general, and if I was to apply Cramer's rule to the resulting system of linear equations, then the denominators prescribed by Cramer's rule would both be 0. A 0 denominator is bad. That means that that system of linear equations doesn't have solutions. So our conclusion is that these two functions, y1 and y2, do not form a fundamental set of solutions for this ODE. You can check that both of these functions are solutions to the differential equation, but actually if you look at them, y2 is just a scalar multiple of y1. So if we were to try to build a general solution out of these two building blocks, what this Wronskian calculation is telling me is that that general solution would not be robust enough to enable me to solve for coefficients C1 and C2. Here I've stated that conclusion in a slightly different way. If I was to try to build the general solution as a linear combination of these two solutions, that function could not serve as a general solution for this ODE. Let's take a look at another example. I'm still dealing with the same differential equation. Here it is again for reference, y double prime plus y prime minus 6y equals 0. And if you were to try to solve this differential equation on your own, these two solutions, the two provided here in part B, are the two building blocks that you would probably use yourself to try to construct a general solution. So let's calculate the Wronskian of these two functions and see what sort of conclusions we can draw. Here's a quick reminder of the general structure of the Wronskian. Plugging in our specific y1, y2, y1 prime, y2 prime gives me this. Now let me evaluate this determinant. Again, to evaluate this determinant, I'll multiply across this diagonal. E to the negative 3t times e to the 2t gives me this e to the negative t. Now I've got that coefficient 2 in front. When I multiply across this other diagonal, I change the sign. Let me simplify this expression. So the value of our Wronskian in this particular case is 5e to the negative t. As you know, exponential functions are never equal to 0. So our Wronskian is non-zero for all t values. That means it's non-zero on any interval of t values. That means that these two solutions will serve as a fundamental set of solutions on any interval of t values that we want. This implies that if we want to use these two building blocks to construct general solution, the resulting general solution will have enough structure, will be robust enough that we can solve for any coefficients for any arbitrary initial conditions. This comes as a relief because this is the general solution that I would have built. So based on the methodology from previous sections, this is exactly the function that I would have built as my general solution. And this calculation here just confirms that on a theoretical level, this general solution is sufficient to act as the general solution. Let's try one more pair of functions given here in part C. Here I've written out and calculated the Wronskian for this pair of functions. Real quick, let's just look at these two functions. I've got e to the 2t. I know that is a solution. And then here I've got 2e to the 2t minus e to the negative 3t. So I'm actually thinking of this as one solution. And we're checking if these two, y1 and y2, could be used as a fundamental set of solutions. Here's my Wronskian calculation. I've got some simplifying to do. I'm going to distribute this through, and then remember when I'm multiplying two exponentials, I can add their exponents. Let me do that simplification. Simplifying this expression, I do end up with these two like terms here that cancel, and then combining the e to the negative t's, I get 5e to the negative t again. As we noted in the previous part, this expression is never zero. So since my Wronskian is non-zero, that means that the two given functions do form a fundamental set of solutions. And if I want to, I can use those two functions to build a general solution for my differential equation. Now this is not the general solution that I would typically use, and in practice actually this general solution would be a little bit more complicated than necessary, but the purpose of this example is to demonstrate that there could potentially be multiple general solutions for a single differential equation, and the way that we test is by checking the Wronskian of the building block functions. And if that Wronskian is non-zero, then those functions can be put together to create a general solution for our ODE. In this next example, we're going to once again confirm a technique that we've used from previous sections. I'm supposing that my LHCC ODE has this structure here. If I was to factor the corresponding characteristic polynomial, I would get r equals negative alpha as one real repeated root. Given that I get that one real repeated root, we would want to use these two functions to build my general solution. Are these two functions in fact robust enough to build a general solution from? Well, the way that we check is, as we've done in the previous example, let's calculate the Wronskian of these two and analyze the resulting expression. Here are all the ingredients that we've been given. This is my y1, this is my y2, the appropriate derivatives. Here, for the derivative of y2, I needed to apply the product rule. Let's go ahead and take the determinant of this little 2 by 2 matrix. And this first product, I've just kind of left it as it is. The second product, when I subtracted back across this way, first of all, when I multiply those two together, it gives me a negative. But based on the structure of a determinant, I know I have to change the sign on that. And then I've got these two exponentials. When I multiply them, I add their exponents. I'll do something similar once I've distributed this exponential through. Let me go ahead and simplify this. And sure enough, these two terms will cancel each other out. So I'm left simply with e to the negative 2 alpha t. And no matter what alpha is, this expression here is non-zero for all t values. So I've calculated the Wronskian of these two functions, and it is an expression which is non-zero. And it's non-zero for all t values. Therefore, it's certainly non-zero on an interval of t values. So we can conclude that these two functions do, in fact, form a fundamental set of solutions for this differential equation, and we can, in fact, build our general solution out of these two ingredients. As I pointed out at the beginning of this example, this is exactly the general solution which we were using in previous sections. So this calculation just confirms the fact that that general solution can be used in the appropriate context. As I note down here in this next paragraph, the other two cases, the case where we have real distinct roots and the case where we have complex roots, are addressed in our textbook. So if you take a look at section 3.6 in our textbook, you'll see the calculations that confirm that the solutions which we've been using can in fact be used as general solutions. Two quick notes as I wrap up. In this paragraph here, I just referenced section 3.7. That's a typo. The next section in our textbook is used by the author to expound on the notion of linear independence. Again, this is related to the idea of a basis from linear algebra, and I would encourage you to read that section, but as I mentioned, it's not that these ideas of a basis and linear independence aren't going to be totally fundamental to our approach. And so I'm not going to have a lecture on 3.7. And then lastly, just to give a preview of what we'll be moving on to next, the next couple of sections will address non-homogeneous constant coefficient ODEs. So we'll still be dealing with differential equations that have the same broad structure. There will still be constant coefficients. They will be linear, but the right-hand side will no longer be zero. If you remember, since the right-hand side of our differential equation was zero, we called that differential equation homogeneous. So in the next couple of sections, we'll relax that restriction and develop some techniques for solving that type of differential equation.